Great. Okay, I'm very happy today to welcome Professor Kristian Kersting from TU Darmstadt. He's a professor of AI and machine learning there, and he's also the founding co-director of the Hessian Center of AI. I see it on his background as well there. And he received his PhD from Freiburg and then was at MIT, Fraunhofer, University of Bonn, and Technical University of Dortmund. He's currently, he's a URAI fellow and an Ellis fellow as well. And his PhD, it received the German AI Award and also the URAI Dissertation Award. He has also co-chaired several top machine learning conferences like the ECML, PKDD in 2017 and 20, and also the UAI, the AI conference, Uncertainty in AI conference in 2017. He has a nice book on statistical, there you go, relational AI. And I believe he has another book coming up soon, or whether it's already out, I don't know, on lifted probabilistic inference. In terms of outreach and broader education and service, he has co-edited one of the first German introductory books on AI for Germans in the audience to read. And he has also started a monthly AI column in a German newspaper. And with that introduction and thanking Kristian for agreeing to give this talk, I give it to Kristian. Kristian, go ahead.
Thank you, and thank you for the invitation, and thank you for joining. And because we just discussed, I'm happy if you ask question at any time, right? I'm actually happy if we just move to the next slide and that's it, and then just have a long discussion and lively discussion. So I was asked to give a little bit of an introduction perspective on statistical relational AI and also emphasizing the role of logic. So let's see whether I can really meet your expectations. But as said, whenever you like, interrupt me. So actually, I would love to just directly start with an example. Why maybe many things we are currently doing, at least in statistical machine learning, is not as easy as many people believe. And if you have done in your life a little bit of statistical machine learning, then it's all about the Bayes rule, right? That's what you see here. So if you want to draw a conclusion, let's say you want to classify given some data, and you would like to compute the most likely label class given some data, then you can't directly do it. So you make use of the Bayes rule to rewrite in order to get terms that you can easily estimate and make use of. Right, that's very standard, but imagine that you would like to do this now in a more complicated setting. So maybe also related a bit to Corona. What if you would like to predict the effect of a drug on a particular patient, but now the evidence is the whole patient's electronic health record? Then it all of a sudden becomes more complicated because you have a flexible representation at hand, right? The electronic health record or the entry, for some people, hopefully it's short. For some other people, unfortunately, it's longer, or it's maybe actually good that it's longer because that means they have been to the doctors quite a lot, but for the regular checks, right? But you can go even further because if you develop drugs, you may also have to look at the whole population, right? So now, imagine that we want to condition on all people in the world, and you can ask similar questions in other situations, like, let's say we would like to understand something about students at universities, or you would like to understand really something in a different scientific discipline. And the idea is that it's maybe not enough to just stay with a single table, but you would like to have several tables and you would like to have relations between these tables. So you want to make use of logic, at least in terms of representation of your data and hopefully also of your models. But even if you say, oh, no, I'm really one of the big fans of very traditional machine learning, then have a look at this case here. So you have a single table. It's about students. Students are taking courses. They're getting grades. And now you're wondering which of the two students, S3 and S4, do you actually expect to do better? Right? And the problem with standard machine learning is that we all make this IID assumption. So we would treat actually all the different students, all the rows in this table as independent. And so we can't really distinguish much these two students. However, if you look a little bit more closely, then you will see, because there's an implicit relation in here, this student took this course, and then you can compare the student within each course to the average grade or the grades you have observed in the same course from other students, you can actually expect that the one student is actually, you would expect to do better than the other one. So I hope these two very simple examples, and we will see some more real-world examples also in the talk, convince you already that what statistical machine learning and deep learning has done is amazing. It's fun to do that and to work on it. But in the perspective, I think we have to develop much stronger techniques in AI and machine learning that can deal really with these complex and structured data. So in a sense, the punchline, the summary is something like statistical AI and machine learning need data and program abstractions. And because we talk about logic here, it's really much more about looking also at logic. There's maybe also a formal argument why you want to make use of logic, because we want to do reasoning here and we want to maybe have modular reasoning engines, and then really logic is what you want to use. But actually, if you ask me, in the end, we may really need combinations of different programming languages or knowledge representation languages and so on. But that's maybe what we can talk about in the discussion. So given logic, what I want to illustrate a little bit here is this, what we wanted and have worked on in relational probabilistic modeling. This is taken from the book with David Poole and Sriram Natarajan and Luc Derat. And essentially, it's like when you look at the literature per se, and in particular in an AI introductory class, you hear something about propositional logic, and you may hear something about probability, and also maybe a little bit about predicate calculus. But actually, we would like to combine all of that. And this means you either have to introduce quantification, right? The notion of variables and quantifying over the variables. So if you go from propositional logic, we arrive at something like predicate calculus, or even at some first order logic, or you put on top some parts of dealing with uncertainty using probabilities, and then you arrive maybe at probabilistic graphical models. And relational probabilistic models, now motivated by the two examples, want to do both again together. So you get something like a relational probabilistic logic or probabilistic relational logic. And I want to make this point very clear from the beginning. That's not a new idea, sure. I mean, there are also negative examples if you really want to get a probabilistic characterization of logic. So this is not what statistical relational learning and also statistical relational AI in the end is about. Of course, we are also interested in these results, but we also take a more pragmatic view on that, right? So it's not about now getting a distribution that holds even for any kind of model in a first order logical setting. It's fine if we, for example, can just deal with a finite case. So keep that in mind, that we want to be a little bit more pragmatic, but that doesn't mean that we don't want to touch even on the more complicated part. So this is the summary, in a sense, of the talk. So let me now try to go a little bit more into details and to motivate many of these parts. So in my opinion, this is really this fascinating vision pushed forward also by many in the UK and also by many in the US, that we would like to have the third wave of AI, right? So in the, let's say, up to the 80s, we can even debate that a little bit, but everything was more or less handcrafted. So in order to get a computer program that shows intelligence behavior, you really had to write down and you have to consider all eventualities. Now, what we experience, at least in mainstream and also in media a lot currently, is the success of statistical machine learning, right? Of learning in general. So given that data is now ubiquitous, we can try to understand this data, make use of this data to build complex models. Of course, we may have to pay some price for that, but it's amazing because there's so many things where coming up with a clear definition is maybe hard, at least by hand. However, that still doesn't mean that we should forget about everything else, right? Data is not everything. And in particular, the third wave of AI is aiming at AI systems that can acquire human-like communication and reasoning capabilities with the ability to recognize new situations and adapt to them. So there are many goals in there, and you see we need many of the AI communities or sub-communities to really help to achieve this goal. And of course, we also have to reach out to other communities to really understand, I mean, human-like communication, that doesn't really work if you're not talking to, let's say, psychologists, cognitive scientists, or even communication scientists, right? So definitely we also have to get in touch much more to other communities. And I think this is also exciting because you get challenged, but you get also pushed to the next level. But for this talk here, it's in particular about the reasoning capabilities. And you see reasoning logic, right? It's a good match. So why is that the case? Well, we all know deep neural networks. They are really amazing. I mean, essentially, they are all about differentiable programming, right? Instead of writing down the algorithm and describing really in detail all the eventualities, you sketch essentially an algorithm, and quite often a simple algorithm. And these are these little networks. And now, after you've programmed, you make use of gradient approaches to fill out the details, to specify the details in a sense, to make the choices you have done without really considering your problem at hand completely, done by data and the machine together. And that's why it's actually called differentiable programming. And with this, you can do quite a lot of interesting stuff. I mean, you all know by now, I guess, AlphaFold 2.0 and previously AlphaGo and AlphaZero. And we also managed to be the world championship looking at Crazy House. Crazy House is a chess variant where when you capture a piece, you can reintroduce it on your side at any point later in the game. And that makes it much harder than the standard chess variant. And unfortunately, you can't directly apply the AlphaGo and AlphaZero architectures, at least the ones back when they were introduced. But you had to, as always in deep learning, massage a lot to get the right architectures together. Currently, we also try to improve the Monte Carlo tree search, actually going for a graph search around it, because you have to always work, and your problem at hand is not typically what is sold on media. You know, just use a black box. It does everything for you and it's solved. There are also some other downsides to deep networks. So I guess all of you have heard about biases in there. Several different forms, right? So you can talk about the biases, for example, the stereotypes that they just copy from us humans by reading our text, the text that we have written. I think that was a very impressive, cool work. But unfortunately, also in the discussion, it was somehow always discussed like machines should now be bias-free. And I think that's also not good, because they are also good biases, but I will not talk about this in this talk. But we were working on machines that make use of similar techniques to actually show that our normative values or the ontological moral values are also captured in these systems and can also be extracted. So it's actually good that these machines maybe we are able to teach implicitly our machines that it's not good to kill people and similar stuff. Anyhow, you know, and it's brittle, and you may add somewhere some weird pixels, and then all of a sudden everything change in terms of interpretation and classification. So there's this big topic, how and whether we can trust deep neural networks, right? And there's a lot of work on that as well. And then trying really to do a lot on explainable AI, trying to figure out what is the input that really led to the decision. But I think there are also current problems that are very tricky to address using deep neural networks. Because deep neural networks, they don't have a full probabilistic semantics. I mean, some of them have, but per se, they are just differentiable functions in a sense that you just try to learn. So at best, if you use something like a softmax as a conditional distribution, but not a joint distribution. So let me illustrate that. You take an MNIST example, you train on MNIST, and you could evaluate on MNIST, and you get most likely something like 100%. But now you're evaluating it actually on other images, where there might be numbers, if you're lucky, but also on any type of other image that have the same input resolution. Now, the problem is that because you don't have a probabilistic model, if you try to compute something like what is getting as close as possible to the likelihood, then actually, if you look at these numbers, you see that they are all peaked at the very same spot here. And that means, keep in mind that this is also a logarithmic scale, that the deep neural networks, because they were trained in a conditional way, in a discriminative way, they can't tell the different data sets apart. So in my opinion, dealing with joint distribution is still very much at the heart of machine learning and AI. And if we have a joint distribution, then also explainability is much simpler because we can ask any type of queries. So that's why I think we need something like deep systems that know when they don't know, right? That's really, in my opinion, quite important. And there's a lot of interesting work in recent years on what by now is called probabilistic circuits. And the connection here is, let me just remind all of us, is that it's essentially like you start with propositional logic and you put probabilities in there. But now you're not doing it in the classical way as Judah Pearl and so on, via probabilistic graphical models, but you just try to carry over or make use of what we know already from neural networks and also try to get a computational graph, right? But it's this first step in statistical relational AI or statistical relational learning. So this work was originated by Adnan Darwish and also by Pedro Dominguez. And as said, you can really view a probabilistic circuit. There are different variants for that. But let's say, roughly speaking, in particular, if we here focus on some product networks, you could view them as computational graphs that encode how to compute probabilities, and to be more precise, joint probabilities here. Right, so you have as input your random variables, well, the states of the random variables, and that now it means as kind of activation functions, you just have sum and products. Sum and products because the product is something like independency and the sum is something like conditioning or mixture models. And at the end, the network computes you the joint distribution. So let's see how that works. And by that, I also hope that you see that you can do similar stuff. Of course, if you do not have a joint distribution, but a truth table. And this has an even much longer tradition, right? If you think of OBDDs and all the other decision diagrams that have been used to represent compactly more logical functions. Right, but you see the same is happening here as well. So we have a joint distribution, or you think of it as a truth table. And now instead of working with a tabular representation, we go for a polynomial representation, right? So we write this table by making use of indicator variables that tell us in which of the rows we are. And then you put the probability correspondingly. You sum together, and now you could say, if I just want to have one single row, well, I can just pick the one by controlling the indicators, right? So you see that there's always this correspondence between rows and entries in the formula here in this polynomial, right? And then to make it look even more like a weighted logic, let's drop indicators because they were about truth values. And so then you see this is a little bit like a weighted CNF, just written in a more functional way. But you can now do everything now, well, many interesting queries can now also be computed in a tractable way. So for example, if you want to sum out, that means we want to marginalize, right? Then I only have to make sure that I'm pick the right rows that I'm interested in. So here, for example, I would like to know what is the probability for x1 being in state 1. So I should have a look at all the rows where x1 is 1 and sum over their probabilities, right? So this is exactly what I can do by setting the indicator variables that we had correspondingly. So we say x1 should be true. So x1 as indicator is true. The not x1 becomes 0. And for x2, I'm saying, I'm not sure, both are possible, right? So you put a 1 to both of them. So you just modify your input, you make a pass through your network, and you get the result. And you can see that, or you can imagine at least that you can do very similar stuff now if you just would like to focus on logical formulas, at least simple logical formulas, right? Now, instead of working with this more mathematical functional representation, you can also turn that into a more graphical representation that is a computational graph. That's just the detail and making it also more connected to what is going on in deep learning. Now, why is that interesting? Well, like with deep neural networks, you can also play now this idea of depth, right? So if we look at the parity function, instead of going for the standard shallow representation, you can now also make use of recomputations in a sense. And by that, your network, instead of being shallow, becomes more deep. And all of a sudden, you get a more concise representation of the problem at hand. If you're interested in that, you can have a look at the library that we are trying to push and develop further. It's interesting because if you think about what we have done, we still have a polynomial representation, right? So you can do even symbolic rewriting operations on that. You can actually compile to other languages because it's just code that tells you how to compute a joint distribution or even marginal distributions. So you can imagine that you can even compile it directly into C++ code, which is sometimes really beneficial because the compiler can make sure that it's highly efficient code. You can directly compile to GPU, but you can also compile to FPGAs. And we are currently submitting a paper where we want to compile on new versions of FPGAs and similar stuff using MEM resistors, right? So you can also try to think of new beyond von Neumann architectures. And by that also get new chips that may support statistical logical queries. The other part is that indeed you could also do learning. So learning means now, how can we get these computational graphs automatically from data? How can we automatically learn a weighted CNF or a CNF from data? What we are doing here is we try to understand whether it's also possible to push the more deep neural network style here. So instead of trying to learn really the structure, we were trying to just make use of random structures, and it works. I mean, although we make some wrong independency assumptions, you can also compile into networks that try to overlap different parts in a sense in terms of these mixtures. And so even the wrong independency assumptions are maybe fine because you can still recover the true independencies by doing the parameter estimation here. So the main point here is only to convince you that if you now have a joint distribution, so you're not looking at the output only, but really at input and output, you can really distinguish MNIST. I hope you see the little spike here from the rest of from the other data sets. You can then also go for efficiency. I just wanted to mention it here because I think there's a lot that we can learn from the deep network community in terms of engineering and how to make hardware, make use of hardware for your computational issues. And I think this is also very exciting to see how much we could do maybe for arithmetic circuits and other more compact representation for logic also on our side. Here we were making use of the deep network in terms of einsum operation that was showing to allow us to scale even further. However, AI is much harder than just going for a simple deep neural network. And let me try to illustrate that next to the examples that we have seen already. So imagine that you would like to predict something like the risk or the probability of having a heart attack. Now, the mainstream machine learning would say, okay, give me a good Excel sheet. I mean, it's a data matrix. And then we try to learn a statistical model that is predicting the probability for a heart attack. Now, actually, the information that you get from medical doctors looks rather more like a relational database. But even this example, also from the beginning, where we said, what about the electronic health record? If you think about it, even a relational database is not really what you want because you may have image data in there, you may have lab results in there, and these lab results might even be also temporal data, so you may have time series. You have all kinds of different distributions in there. So it's really, at least for a researcher, a positive nightmare to deal with this type of data. And so overall, in really to scale to the next level is, as said already, as argued already, is really we need this crossover of deep learning with data and logic programming abstractions. I mean, that's anyhow at the heart of computer science. And it's a little bit frustrating that we are still in machine learning at a level that we feel like we don't need high-level programming languages, although we see the success of high-level programming languages. So here's already one of the takeaway messages. By combining, for example, logic and statistical machine learning, you really help a lot to build more complicated models, but you also help to democratize, in a sense, machine learning. So let me explain that here as well. So imagine that you just go for a deep network and you would like to have a deep network that is looking at movies. And let's say it's movies of cars for whatever reason. Now, actually, if you do programming, you know that you should have unit tests. So you would like to write down something like, if I see a car in frame 1, and I see it in frame 3, but I don't see it in frame 2, then most likely something is wrong. My network is doing something wrong. My deep network is doing something wrong. So you would like now to have general unit tests, and to formulate these general unit tests where you would like to say, for all triples of frames or consecutive triples of frames, you would like to say that if I see a car in frame 1, I see, or X, or well, let's call it 1 for now here, in frame 1, and I see it in frame 3, then I also would like to see it in frame 2, at least with a high probability. So you see that you would like to have a relational rule talking about frames and objects in there, and then saying that certain conditions hold there. So whether you agree on that you want to have logic and probabilities and deep networks combined just to phrase your model or not, that's maybe not even important, but I think it's very convincing that at least on the constraint side, on our unit test side, we definitely need higher order languages, because otherwise you would have to write it down for each frame. And if you think of more, from a semantic perspective, even more complicated settings, you would like to have the AI engineers in the future to just write it down in their own words. And that's where logic can help a lot. But now let's go back to the really more core question again of AI and where we want to all go. And there's this big discussion currently going on in the AI community about thinking fast and slow due to Daniel Kahneman, right, where he was arguing from a psychological perspective that there are these different systems going on. So without going into the details on the psychological and cognitive science and maybe even neuroscience side, I think definitely we need AI systems that can do both learning and reasoning, because it's a little bit frustrating that you say, in order to learn something, in order to do something interesting with an AI system, you always first have to train the system, because that's actually not the case for us humans, right? We learn in certain situations, but we can transfer. And in some cases, if you think of a production site, you may not have any data if something terrible is happening and your production line breaks down, right? That's kind of the definition of a bug. If we would have enough data of a bug, then it's not a bug anymore, in a sense, because it's obvious that you want to avoid it. So reasoning is really important, because there are more situations where you don't have data at hand for the problem that you want to solve. So and this is where these relational probabilistic models come into place. And because I was asked, let me now review a little bit two of the, there are many more, and I apologize to everyone whose model I'm not, or framework I'm not mentioning. But let's look at the two that, in a sense, are maybe most prominent. And the one is Markov logic or Markov logic network. And the intuition here is that you take a logical knowledge base. So you have a bunch of logical formulas. And now, instead of saying there are hard constraints of what is possible, so the set of possible worlds, you see them as soft constraints. So you're just saying, okay, maybe we rule out some of the worlds, but not all of them. And you essentially implicitly count how many worlds are now possible out of all possible worlds, right? So the idea is that you take your formulas and you put a weight in front of it. You get a weighted constraint, and then the probability of a world is, roughly speaking, something like the exponential of the sum of all formulas that are satisfied. So it's a log linear model. A little bit more formal, we have a set of formulas in first order logic, typically, to be honest, because if you have functors and function symbols, it's getting harder typically you look at function-free formulas here, and for each of the formulas, you have a weight. Now, semantically, as said, it's essentially a log linear model. And what it does is it looks at actually how often a particular formula is true. That means you look at the groundings of all these formulas and how often they are true. Of course, you can think of using typed logics here, but let me just illustrate in a very simple way, and these slides are actually taken from Pedro, what this actually means. So let's say that we have 4 possible worlds, right? And then we can now talk about whether Anna and Bob are friends or not, and whether Bob is happy or not, right? So the different combinations, we have 4 of them in total. So a logical rule, let's say if friends Anna and Bob, then happy Bob, right? Which is, if you rewrite it, it's nothing else than not friends Anna Bob or happy Bob, right? Means that we are covering these 3 possible worlds, and we rule out really the one model, the one world that is violating this friends Anna Bob, in the sense of that you say, okay, Anna and Bob are friends, but Bob is actually not happy, right? You completely rule it out. Now, by going over to a weighted logic, or here Markov logic, what you're doing is you're putting a probability there. That means you still assume that it could be a possible world, at least to some extent, right? So it leaves some of the probability mass now on the case where Anna and Bob are friends, but Bob is not happy. So how could you do that? Well, for example, you can put a weight of 1 on all these different possible worlds and a weight of 0.75 on this specific one here. And then plug it into this formula for the log linear model, well, after transforming, and then you get exactly the result. So this is, roughly speaking, what Markov logic networks are about. To make them now more practical, actually what people have done is compiling them to a graphical model, to an undirected graphical model, and then do inference on the graphical model. And what turns out is that typically the grounding is taking much more time of the whole pipeline than doing the inference. And there's still a lot to you can improve, I guess. I mean, given the boundaries of how efficient grounding can be and all these standard problems of, for example, counting how many triangles there are in a database or in a data log program. And these are the standard constraints. Now, the other framework that is pretty prominent is Problog, due to Luc Turat and his group. And Luc was going not for, as Markov logic networks, in a sense, was not going from the graphical model perspective and trying to put a little bit of logic in there, right? That's what MLNs have done. You could say this is just a log linear model. And now as a feature, I'm using the logical clauses. And because logical clauses can have different groundings, you say, hey, actually, I'm counting how often this clause is happening there. Now, Luc was going the other way around. He was essentially starting with logic programming and was trying to put probabilities into logic programming, so into the proofs, for example, right? So that's why he's taking a little bit more of a generative perspective. But keep in mind, in the end, both of them, of course, share many views, and maybe with enough extra variables, you can always transfer from the one in the other. Who knows? So he would like to play a game with us. So in this game is you toss a coin and you draw a ball from each of the 2 urns that you can see up here. And then you win the game if you have hat and a red ball, or you have 2 balls of the same color. So it could be red, red, or blue, blue, but with green, bad luck for you. Now, breathe for a moment and think about how you would make use, or how would you specify the distribution here, right? It's a rather complicated task already, because you have coins that you have to toss, and you have urns, and who knows, maybe you can still come up with probabilities for each of them. but now you get these very harsh constraints when you have a win or not. And it's not even clear that whatever distribution you make assume on coin and earn, how they propagate, so to say, towards the distribution of the win. So if you ask now for the marginal of win, this might be a quite complicated distribution. So instead, if you make use of logic in combination with probabilities here, then actually you can just specify implicitly the whole joint distribution and have a general inference engine that tells you the answer. And that is what was about what I meant when I talked about let's democratize machine learning and AI and probabilistic stuff here. So how can we do this? Well, we just write down in their language in Problog. The probability for heads is 0.5, 0.4. So that means for not heads, it's a kind of closed world assumption, it's 0.6. And then you can write down also the probabilistic choices for your earn, making assumptions here, saying, for example, the color in the first earn for getting a red ball is 0.3, and for blue one is 0.7. And then for the second earn, you have 3 colors here. And now you're specifying the conditions of the win just using standard logical formulas or logic programming code. You simply say, well, I can win if heads is true and the color of a ball, and I don't care about which earn it was, is red. Or I can say I win, or no, not. And I say I can also win if the color of the ball from the first earn is the same. So you have unification going on here as in the second. Now, how to do inference? Conceptually, you go via possible worlds, right? That's this generative view here. So let's see how that works. Well, one world is one of the gray boxes here. So you first draw the whether you have heads or not. Here we got lucky and it's heads. Then with this knowledge, we can continue and take the next rule, and we can now draw the color of the ball that we draw from earn 1. Likewise, we can go for the ball of the color of the ball from earn 2. And now, given that we have specified our knowledge here, we can instantly evaluate our logical formula here, and we get overall a probability, and this probability here is 0.4 times 0.3 times 0.3, right? And so now I can generate the next one, and maybe we are not lucky and head is not true, so it's false. So I have to use 1 minus 0.4, right? And can go through it. And so on and so on. So this is conceptually what you can do. Of course, no one is doing that because you're generating exponentially many worlds here. And then additionally, because you use logic now, even each of the worlds might get, in a sense, exponentially large. So this is not what you want to do, but conceptually, it shows you that you can do now whatever you like. You can go for probabilistic, you can go for probabilistic query. So you just count how often a particular configuration is true. You may also take questions like what is the most likely explanations. You really, I mean, because you have all possible worlds at hand, assuming that everything is finite, you can do whatever you like. However, that is complicated because you have to generate everything. And so actually what the Problog line of work has started a lot then is to think about the semantics and how to make use of the semantics in a different way. So what is the semantics showing? Well, the semantics is essentially showing us that the probability of a query is something like I have to look at all the rules that have been positively evaluated, or I'm drawing from my probabilistic facts, right? Together with these Prolog rules. And then I'm just looking at how often these facts have been true, respectively false, right? If they're false, I use 1 minus. So that's semantics. Now to do that more efficiently, actually, you would like to compile to something, right? And for example, you can compile to a weighted CNF. So again, you may have a probabilistic program here. You're wondering about the probability of win. And then what you do is you first try to understand which of the logical rules are really important. And that's what you can do by some backward chaining approach. And then you can extend this now together with the information that you have. And for example, via Clark completions, you can turn it into a CNF where you can now run any weighted CNF solver on that. So let me just detail that without going into all the logical details, but it's really important for me that you here make use of something like Clark's completion, and in a sense accounting for the negation as failure. Why is that for me important? Because again, it shows you that logic and what has been developed in the logic and well as logic programming community is really important and can help you to push AI to the next level. So, and this push and that you can do amazing things if you just combine these different things, different worlds, it's also true if you really think about what is going on here. Because why do we want to have logic? Well, we would like to have logic here in order to first compactly represent things, but also to do our inference more compactly. And if you would like to know more about one approach, which is called the knowledge compilation, so this is an extension of all these arithmetic circuit ideas, now even to the first order or relational logic level, then you should check out the work by Guy van der Broek, and also Adnan Darwish did something in the early stages there. But there's another connection. And again, in a sense, logic plays a major role here, because for some of the logics, particularly if you're interested in approximate inference, you can use what is called the Weisfeiler-Lehmann algorithm in order to figure out the symmetries and exploit them at inference time. And this Weisfeiler-Lehmann algorithm is actually an old algorithm that was also sometimes named naive vertex classification. And it's interesting because you can use logic, and in particular counting logic, in order to capture the expressive power of the Weisfeiler-Lehmann algorithm. So again, logic is very central here to understand what is really going on. But let me also illustrate to you the Weisfeiler-Lehmann algorithm and how to make use of it in order to make more efficient inference. And that's an example that is coming actually from real world. So Guy van der Broek, when he developed his first system, he got from one of the users this question of, wait a minute, can you help me? Can you show me how I can solve this problem here efficiently? And in the first version, if I recall correctly, it was not working very well. But then with some technical contributions, actually, one could solve it amazingly fast. And the problem was the following. It's very simple. It's the question, what is the probability that the first card of a randomly shuffled deck with 52 cards is an ace, right? So you shuffle your cards and you just ask now, before turning around, what is the probability that the first card will be an ace? So think about it. I guess for all of you, it's very simple to understand and to compute that in a split second, right? There are 4 aces. There are 52 cards in total. So it's 4 divided by 52. Very, very simple. Now let's see how AI technology would do it. And if you go for probabilities here and you make use of a graphical model, then actually you would have to code that there are 52 different cards, right? So you have a card could be at position 1 up to position 52. And you have to code somehow the value of the card here. Now, probabilistic graphical models, without having introduced them, they are all about coding the independencies. The problem here is that in here you don't have much of independencies, because when you know that the first card, let's assume, would be now a diamond 2, then the probabilities for having a diamond 2 at any other position, of course, are changing. But also the probabilities of having a different color or different value, different card at any other positions is also changing. So essentially your graphical models look like a monolithic big black box in a sense, because everything gets connected to everything. And that means you have something like 2 to the power of 2,700 states. And this is definitely more than there are atoms in the universe, at least according to the estimates of the physics people. And this is like, he is also always pointing out, it's a little bit frustrating, right? We have all this amazing AI technology, but still computers can't even solve it, no matter how many computers, how many things you do here, at least if you model it this way. So it's really frustrating that this a machine can't really solve this problem without being a little bit smarter. But obviously, somehow I have tricked you here. So what is missing? What have I tried to hide here? And the main problem is, or the main insight is, that position in cards are exchangeable, right? If I ask you instead of what is the probability of an ace in first position, what is the probability of having an ace in the second position? It's the same answer. Third position, same answer. Last position, same answer. If I replace the ace by any other value, let's say what is the probability that I will see a 2, same answer, right? So there are tons of symmetries in here, and we have to make use of exchangeability. So again, if you make use of logic, actually, instead of having already this super large graphical model, you just need 2 rules here that are weighted. And these 2 rules are just telling you, well, if you look at, if you look at, if you could say that that the same value appears at different positions, then it should have been already the same value. That's essentially that you code here, right? So you do that for both of them. In the one case, you say, if you have the same card at the same position, different values, then it has to be already the same value. And in the other one, you say, if you have the same value at different positions, then it has to be already the same position. So 2 rules, weighted, very concise, very compact representation, and only because we make use of the notions of objects and also of logical formulas to code our knowledge. So, but this fast modeling is only part of it, because you now need also fast inference. And as said, there are other techniques, but I would like to illustrate here a very simple one, which is based on this Weisfeiler-Lehmann algorithm that has been used in particular with approximate inference techniques. And the idea roughly is, instead of working with this super large model, imagine of the cards, you still, if you look at the ground model, you still have all these ground atoms and also all these ground clauses. And so you have to deal with that. So and somehow the idea is that the machine now, like a compiler, is automatically, from the description at hand, compiling to actually the smaller model. So how can we do that? It's rather simple. So if you have a graphical model, you can also represent that as what is called a factor graph. And because we want to talk about logic here, a factor graph is nothing else than a weighted CNF. So what does it mean? Here are your proposition, or in our case, random variables, but in logic, you would have just your propositional variables here. And here you have factors that are coding the CNF, so both the logical structure as well as, in our case, the weights in there. Now, in the beginning, let's say that we just want to have the probability for each of these random variables. We can't distinguish them, because without knowing that they are in part of a particular factor, they are indistinguishable, right? So I can give them all the same color. Now, additionally, I may know that all the color factors here actually are the same. So this is coming from the logic program that we have specified, and you can easily see that this factor is a ground instance of the same clause, right? So you can get that information as well. Now, what you could do, what you can imagine is that instead of running probabilistic inference, you simulate it by sending around these colors here. So A and B are sending the red color to F1, and B and C are sending red color to F2. And then these factors are taking it, they're assigning it with their own color, and they send it back. What have we learned? Well, A and C are indistinguishable even after one round of communication, because they just communicated both with another red random variable via a blue factor. Only B is different, because B is actually sending and receiving 2 messages. So we can assign a new color to B because B is somehow different, and then we could iterate again. In this particular example, after this iteration, nothing is changing anymore. And you can see from there that actually you can compress the overall model, because instead of using the original model, you can compress it by saying you put A and C into a kind of supernode. They are indistinguishable. And then you have to massage a little bit the original formulas. Let's not go into details here for this message passing in order to get your belief, or you could also say for solving your CNF, weighted CNF in a message passing fashion, but that's it. And so you can directly exploit symmetries in your probabilistic as well as SAT solver, respectively, logical inference machinery. Right, so that is what is lifted inference about in the end, that you really take a big model and compile it automatically, in a sense like a compiler to a smaller model.
Hey, Kristian,
Yeah,
just you asked me to give you a warning, so I'm telling you we are
yeah,
like 5 minutes from the hour, so you can probably talk for a little bit more, five, ten
perfect
minutes from the
timing.
hour. Yeah.
Great, thank you. This has been explored, and also the learning, so we can also learn the logical rules from data. And because I was talking a lot about electronic health records, let me just prove that you can really do it. So we applied this whole machinery that was developed to actual electronic health records, so actual patient data. And it was about the prediction of heart attacks. It's a longitudinal study, the CARDIA study running in the US, running already for, I don't know by now, 40 years, 45, maybe 50 years, I don't know, where patients are coming to the hospital every 5 years and they get checked and they run some tests and to understand the different factors on heart attacks over time, right? And so we learned now, let's say something like a Problog program or a Markov logic network. Actually, it's a so-called relational dependency network, but that's a detail here, for predicting these heart attacks and the risk for it. And people were happy, in particular the medical people, because our first decision here, so it's part of the model, and it's based on decision trees that actually deal with probabilities. And the first decision, which is also the most informative one, was actually on gender. And that is what is known already from the medical statistics, that you know, females and males have different statistics when it comes to heart attack. And then you can dive deeper. And then we had in the beginning a bit of a hard time to sell or to justify that cholesterol values are actually more informative than whether you're smoking or not. The funny part is that you can learn that in just 9 seconds by using what is boosting. But main point again is not about the details. It's just you can do statistical machine learning on a complete database, and that can be very efficient. And because you have a probabilistic relational model, you can do reasoning afterwards, and maybe even ask something like, what is the probability of having a high cholesterol value, given that you know that you're smoking? If you're interested in, you can also download our code, also with some other parts in there, for example, like how to get the human in the loop in there, also when learning. But yeah, please give it a try and tell us if something goes wrong. So generally, this is also, I guess, why so many companies are actually interested in combining logic and probabilities, and by now actually also deep learning. So there's a lot of interesting work on probabilistic and deep logic programming. So really trying to unify all the different major approaches in machine learning. And because if you recall how deep learning was boosted, it was when they acquired DeepMind, right? And then it's always said that DeepMind, maybe that was about 300 or 500 million, the acquisition. The investment into this probabilistic programming, deep probabilistic programming stuff is way already at 800 million, and probably by now even more. So I really strongly believe that this will also be a revolution in terms of AI engineering, but also will really help on the scientific side to really understand how to combine learning and reasoning, and by that also make contributions to cognitive science, psychology, but of course also being motivated from insights from these other disciplines. And this is why there's also so much interest, and there was, maybe you attended it or you've heard of it, this discussion between Joshua Bengio and Gary Marcus. But I hope, as I have convinced you, there's much more already on the stack and has been done than what is typically discussed, but there was a very interesting second debate, also pushed by Gary. And I think it's very important because it's really important to get with other disciplines together. And there will be yet another one on this Sunday, and I can only welcome every one of you to join, where we will also discuss that, and with Marta, Leslie, he, Louise, and Matthew. And you see that we tried to get a good mix of people, right? Maybe people that push a little bit more the pure deep neural perspective than other people saying, oh, but maybe symbols are great because this helps us in certifying things like Marta. Then actually Leslie will say, oh, come on, neural symbolic is not new. And I don't know whether we really need this new term, and do we actually need it at all? That's maybe what Leslie will push for. She being having made so many contributions also in probabilistic lifted inference, providing this perspective and the connections to databases, and then Louise Lamb, who actually worked on combining neural network and logic already for centuries. So with that, let me conclude. AI is really much more than deep neural networks. Don't get me wrong. I enjoy deep neural networks. They are pretty fascinating. They are powerful. They have really pushed the field. They made it so much easier, in particular because of all this engineering efforts, making it easier to come up with deep neural networks. That's pretty good. But they are not the end of the story, because logical, probabilistic, and also causal models are kind of white boxes, right? They typically provide, in a much easier way, insights into your application. But just from a practical perspective, most data actually is stored in databases, right? So a single table is not enough. We really have to deal with the complexity. And again, from an engineering perspective, that's what you see also in TensorFlow and PyTorch. We all, of course, use for loops. So let's take that serious. Because we talk about knowledge, we also need logic in there in order to have a modular representation of knowledge. So summarizing, in my opinion, logic will play an even bigger role in the future of AI. And that's why, again, thank you for the invitation. I'm looking forward to your feedback. But let's really just go for the next step. Let's try to reach the third wave of AI. There's so much to learn, so much to do, but also so much to win. Thanks.
Thank you very much, Kristian. And since I'm speaking, I can do an actual applause for you. Okay, so let me open this up to questions from people. And while we wait for people to either raise their hand or say something in the chat, I am going to say that I would probably agree with Leslie.
Yeah. I mean, that's why I've pushed for her, because we invited her. I asked her, and then she said, I don't know whether I should join, because maybe I'm just saying we don't need it. It's not new, whatever. And I said, Leslie, that's why we are asking you. I think that's a very important part of the discussion, right? I'm with you. It's just interesting to discuss per se.
Any questions from anyone in the audience? Or I have questions for Kristian, but I'll probably leave this open to the audience first. I don't see anything in the no raised hands. Anything in the chat? Okay, so if they are not going to speak up or they're thinking about it, maybe I can get started. So okay, so Kristian, so this was a nice way to link things up, and this was a nice talk. I liked it, and so I have a couple of questions. So maybe I'll get started with one. So you talked about these different kinds of ways of introducing logic into it and stuff. And I know you can't, as you said, talk about all the different frameworks and approaches possible. So I was thinking, could you talk a bit more about different uh, the kind of things that are done with these sum product networks and other kinds of things? These are more like logical constraints or other things, right? You could introduce the constraints and stuff. So what if I had, say, general statements, like the thing that I like as a roboticist is notions of default statements and other things. What are some ways people have, say, tried thinking about this? And because I think you're the right person to ask about this community to speak for this. And what are some ways you think it could be done?
So maybe you can correct me. I mean, it's interesting, but as far as I know, of course, first of all, having probability, you can also think of some default logic,
Mm-hmm.
because you have already probabilities. But I think what you were asking about will push this even much more, because we go really into tricky application areas. So I can only tell you, so another prominent approach is probabilistic soft logic.
Mm-hmm.
I think this is then maybe already covering most of the approaches from a logical perspective, because so PSL is due to Lise Getour,
Mm-hmm.
and what they are doing is they say, okay, actually, many of the logical formulas that we see can be again interpreted as constraints on my objective function, but now making use of this continuous representation that is coming from fuzzy logic. So they use a Lukasevich norm or whatever. And I like that, because this is actually what you were saying, make it much more obvious that we talk much more about the constraints. So I like that. Now, next to your work, and maybe the work by Marc Toussaint, and Marc Toussaint was pushing for yet other languages that are maybe pushing more the continuous part, and how to get for robotics planning problem
Correct. Yes.
that stuff together. I would argue that we should just unite efforts and push for it, because what you just said reminds me of what I said with the unit tests. And for me, robotics is a perfect setting, and I have no clue how to really do it. I think there you are much more the expert than me.
Okay. Someone has their hand up. I had something follow, but I'll wait. Let's give this Leo. Could you speak up, please? Leo Bertossi. If I'm sorry if I'm mispronouncing your name, but please speak up with your question.
Thanks a lot. Yeah, very interesting presentation. So I have a question about the probabilistic logic programming approach. Is it possible to include recursion in those programs? I mean, would it make a difference in terms of? I mean, you talk a bit about the Clark completion that is complicated in the presence of recursion, for example. So that's why maybe you can comment on the need for recursion, and if it is already, I mean, some development that includes recursion as well.
So yeah, definitely you can have recursion. Of course, then all with the little tricks that you need also from logic programming perspective. But for example, an easy trick here is that you assume that you have recursion, but it's a safe recursion in a sense you have no infinite loops. So it's the same stuff as in Prolog. If you really have an infinite loop, you're screwed, right? So that's what I also, I guess, meant a little bit in the beginning, like, let's be a little bit pragmatic here, and just to see how far we get. And I mean, that has been, we have been pragmatic for the last 20 years, the community, or 15 years. But I think there are now new interesting challenges, and you can now wonder whether you can also maybe make Clark completions more interesting by viewing it as a probabilistic task, and trying to make use of this iterative convergence and make use of the probability to see should I extend or not, right? And now maybe, I'm not sure that I'm interpreting it the right way, but to be honest, none of us, and also none of the neural symbolic people, have really made major contributions to this old problem of how to move between the discrete and the continuous world. And this is, again, I guess, no matter what you will ask me, it's one of the major problems also for the Clark completion, in my opinion. So there's always this trick of saying everything I'm looking at is finite, and then we don't have, I mean, there are still other issues, but we don't have that particular issue. But I think this is where we have to work more on. So in the machine learning and deep learning community, there's a lot about reparameterization. So essentially, it's like you want to rewrite a probabilistic program in a more deterministic fashion, but you could still do gradient estimation. but there's even only, as far as I know, only one paper by Stefano and more on showing how to do that with a discrete distribution, because you can't reparameterize. So there are so many still issues open. And similar, if you there are approaches that argue we can have a neural network that is learning the shortest path. And yes, it does it on the graphs that are considered for training, also on graphs that are similar to the stuff that has been used for training. But the cool part about an algorithm, a deterministic algorithm or discrete algorithm, is that I can actually run it even on graphs with 1 trillion of nodes. And you still know it's true. And I think this is where the problem is with the differentiable programming, because you have to, you can't go for 0, x, or 1, but you have to go for something between 0 and 1. And now if you have long computations, these values may vanish, right? And it's only a question of how big you want to make the computation. So no, as far as I know, there has been no push also on the Clark completions back to, so to say, to the logic side. So far, it's typically we have similar issues and we live with that, but we are aware, but we can at least introduce it to the more statistical machine learning community. On the other hand, if you check what Moshe Wadi and also He van der Broek and Dan Sucho are doing, I think there are some breakthroughs in, for example, the way of counting triangles, and that again helps you also with probabilistic inference. But we have to push further. That's the main point.
Thanks a lot.
But you can have recursion. That's exactly the benefit. I mean, you can have, of course, recursion also in Markov logic networks, but in Problog, it becomes obvious. You can have any Problog program and you have to live with the problems of Problog. But that's the nice part. You can have conditions on equivalence, right? And that makes it so hard from a probabilistic perspective to model a priori in a parameterized fashion. Yeah.
Sorry, anyone else with any questions? I don't see anything in the chat. If anyone else wants to ask a question from Kristian, please put your hand up or type something. Okay. Oh, cool. Nobody. So I can ask mine first while I wait. So a question for you. At the sort of the EKI, right, conference earlier, or should I say later last year. So Luke gave one of these invited talks, I believe, on this, trying to do this Problog with deep neural stuff, right? So I was wondering that if you could, I mean, you talked a bit about that. I was wondering if you could, for the audience in general or something, talk about some of the probably challenging things that people could look at when you take something like Problog and go into the deep neural nets.
Yeah, I'm super happy to do so. So first of all, we have also worked on it, and we have extended Problog to also make use of SPNs. But anyhow, okay, so what is the problem there? So I'm not sure whether you've heard of it, but there's this data set which is called multiple MNIST, and maybe that is a good way to illustrate what you would like to do in the end. So imagine that someone gives you images with little arithmetic problems. So you say something like 1 + 1 = 2, 1 plus 2 = 3, and whatever. Now you would like to have a system that is reading this image, solving, telling you whether this equation is correct or not, or maybe even solving if you have a question mark somewhere, right? So you could say 1 plus question marks equals 2, and you would like to know it's maybe 1. So you would like to have these kinds of systems, and there are different approaches to that. Of course, you can first try to push everything into a more complicated deep neural network. And so you may combine some convolutional network together with maybe by now transformer or graph neural network in order to solve that. You could go for what Josh Tenenbaum is doing, and we are currently also exploring, saying that on one hand, you may learn several CNNs to figure out the different objects, the 1, the plus symbol, the equal symbol, the 2, the question mark, map it, so to say, by that to a symbolic representation, and then you combine it with a probabilistic program. And this is also what deep Problog is about. Ultimately, of course, you can also do what Josh was doing with deep Problog, but what deep Problog is saying is, okay, why not saying that some of our predicates are actually represented by a neural network? So instead of recall, I can go there maybe. Here. Right, if we turn that into the program here, then we had these probabilistic facts here. And now you could say, okay, this probabilistic fact here actually, or all of them for color, they become a neural network. And that means when we start reasoning in here, at some point we may hit in our proof the neural network now instead of a probabilistic network, probabilistic fact. And then you ask whether you can see in there, let's say the color, the symbol 1 and the symbol 2. So you may have image here, and then that this is symbol 1. So the image goes in here, and here you get the interpretation, what you see there. So what is the nice part about that? So first of all, you combine different multiple modalities, which is interesting in many applications, and we humans can do it. So it's an interesting question how you can do that in general. Computationally, it's interesting here because you are now combining a computational CNN together with a CNF in a sense, right? Or several CNNs with a CNF. So the question is, how do you bridge the two worlds? And in deep Problog, that was this question of, can you have backpropagation through the logical part as well, but without being fully differentiable? So I think this is a very exciting direction now, to ask also whether we should actually make use of fully differentiable Prolog there. And there has been work by DeepMind on that, by many people, also Sebastian Riedel. So that might be one interesting direction. But I think from a semantics perspective, it's also interesting because Problog, this deep Problog is, in my opinion, actually a conditional distribution, because it makes use of the CNF. And it's just asking for the probability of the label. So it really just makes use of the output of the CNN. But actually, I would like, as argued also in my talk, to have a full distribution also about the input, because ultimately, I would like to have something like that I symbolically maybe write down 1 plus x equals y, and then it's automatically generating also the images for that. Or I provide an image for one part, and then it generates me the symbols. So the big problem behind all of that, or the big vision or the big research question, is what is called the physical symbol grounding problem, right? So because I've written here red, it doesn't mean that red has any meaning. I could replace any of the reds there, as everywhere in logic and in programming, by also unit x, y, z, and it still gets me the same answers. So this question of how can we take a symbol from the computer and ground it in reality, connecting the name Kristian to me, at least when you talk to about me, that's a fundamental problem. And now by combining logic and deep networks, this is the hope that we can connect to our sensor inputs, and that way also to our reality, the logical part, which always had problems there. So that's a big challenge. So if you ask me for things that we can improve, there is a little bit a question of semantics. So why not using also distributions over the inputs? That's why we have pushed some product networks there, but then it's also about the scaling issue there. And then also showing that there's really a benefit, so applications for that. And that always means engineering. I mean, doing that all efficiently, it's pretty hard. So there's this general other question, if we now abstract from that, there's differentiable lambda calculus. So now moving on to the probabilistic programming that is more imperative. There is both the differentiable as well as the probabilistic lambda calculus. And I think it would be wonderful to combine both. And what does that mean from a semantics perspective? And then, as said, can we now make use of Problog within software engineering? And you can use robotics as an example to write down constraints that should be fulfilled. And if we talk about constraints, then at some point we have to move, in my opinion, one level further up, because let's face it, while I like logic, it doesn't mean that everyone on earth is an expert in logic. So maybe we have to even think about naturalistic programming again. So there have been approaches in the programming community, but I think we have to revisit that and also think about naturalistic probabilistic programming and naturalistic deep programming, so that you can program your machines using natural language. And there has been a lot of work that transformers also do learn a bit, for example, so these BERT and GPT-3, a bit of logical inference. And so ultimately, the big thing is that at some point we may get the first positive singularity in AI, namely that we understand that computer vision, robotics, NLP, we all need each other. And actually, we all have the very same vision in mind. But that's far-fetched now.
Thanks, Kristian. Thanks a lot. Okay. Did anyone else want to ask anything?
I actually might have a question.
Oh, Martin, go ahead.
Yeah, so thanks again for the talk. I really enjoyed it. And I like the examples, and they were mostly closed world examples, where it should be possible to formulate all the rules, how things work in advance. But of course, in our open world, we often don't have that, or we have at least differences between the modeled closed worlds and the actual world. Are there approaches that allow to learn or infer new rules based on observations, or maybe to adapt the rules if the open world is non-stationary?
Yeah, so, okay. So of course, there's a whole bunch of structural learning approaches. I mean, structural learning, so meaning we not only want to get the parameters here, the probabilities, but also the rules. So there have been extensions of inductive logic programming approaches around Stephen Muggleton. I mean, originally, to a large extent, originating from Stephen Muggleton and Luc Derat's work. And then you put probabilities in these approaches, but that's pretty tough most of the time. So what we were pushing is a lot of boosting approaches. So you learn essentially a bunch of small rules every time. And of course, you're losing this nice interpretability part here. But we were arguing better to have a model and not to be easy to interpret than having no model, because that's also not easy to interpret if you have no model. But anyhow, there hasn't been as much work, but the boosting works pretty well. There's also some work by Oliver Schulte on more faster learning. Now, the question of dynamic models, of course, you can have something like a dynamic Bayesian network now in a relational setting. There has been work on that. Learning that one is getting really tricky, the structure. So there has been less work on that. And I think this is why people also would like to combine now also deep neural networks and probabilistic programs, because this gives you even more flexibility that you may take an LSTM and combine it with some logical rules. However, you were also touching on a problem that I think is even more important, namely the open world. I mean, all of these approaches that we talked about assume that we know the population, and I can at least name, at least implicitly name, respectively enumerate all of the objects. However, in the real world, imagine you're a company. I don't know how many customers I will have tomorrow. I may not know all the names of my customers, right? If I'm online shop, it's not that I may keep all the names of them, or maybe in an online shop I do, but then I have also a store and there I just have customers and I don't know whether it's the same customer again or not. So there are interesting problems. And for example, Greg Boutelier now at Google, he is also working on that in order to run campaigns. And then how can we deal with this situation that I don't actually know how many customers I have? So this is, I guess, even more important. So there was early work by Stuart Russell on these kinds of open world problems, and it's the block language with Brian Milch and David Sontag, where they looked at a Bayesian formulation of these kinds of probabilistic logics. There was follow-up work on non-parametric logics by David Poole and Nando de Freitas. I think we have to work more on that. And there's very interesting, rather recent work by Guy van der Broek, where he also would like to quantify, in a sense, probabilities over if I don't know all the constants or how many people there are. So open world probabilistic programming, but also open world deep neural networks. Amazing, pretty tough, but really amazing. Very, very nice topic. But as I said, there are structural learning approaches, yes. So you don't have to start from scratch, but whether they are really useful for the robotics part, question mark. Together with Wolfram Burger, of course, we were making use of that. There's a whole work on relational Markov decision processes, and you can have, of course, relational policy gradients. And again, with boosting, because you just want to have a policy, you can push that a lot. And then Marc Toussaint was also pushing that further for some papers. I had also the pleasure to work with him in pushing that further even into exploration, exploitation, and coming up with relational quick variants. And so there is some work, but I think that is all only at the very beginning. Within robotics, next to your group, I think getting in touch with Marc Toussaint is might be a good. And of course, I'm happy to collaborate as well. Don't get me wrong. I'm just saying he's really working explicitly on robotics using relational models, trying to connect much more with continuous differentiable models, maybe even PDEs and so on.
So
Thank
maybe
you.
I wanted to just make one small connection, and maybe we can end with that, given I don't want to keep you here for too long. So one thing I noticed was, like, because I started from the probabilistic side before I got into this, logic side of things. And so one thing I noticed is there is considerable work from the logic programming side, just as the Problog started with saying, I have these probabilities. Now, can I also handle logic statements here? There is work from the logic programming side saying, I have this logical framework. Can I add probabilities to this? So the thing I notice is they don't, not because of want for trying, but they don't have maybe solutions that are as efficient as computationally, but they have nice ways of representing things, dealing with open world problems and other things, or default statements and other things, because that's their strength, right? That's where they come from.
Yeah.
So maybe I would just add this comment of saying, and that's the kind of stuff I started using. And I mean, you've seen me talk before. And so I think what would be a nice thing is for these to meet at some point and sort of get the best of both worlds somehow.
I subscribe to that, but I would go one step further. I would say, look, maybe at some point we should forget about expressivity for a moment and really spend some effort in providing something like the relational TensorFlow
Correct.
or
Okay.
relational PyTorch.
Okay.
Now, I can also tell you that actually relational AI, I think you know the company, right? The one.
Yes.
They are pushing that a lot. And we will definitely start to collaborate. I'm happy to connect you if you like.
Yes, please. Yes. Yeah.
Because look, I mean, the problem is we are both at universities, and we can do a lot at universities, but production style programming and
it's not our job. Yeah.
Ooh, it's tough, right? But that's why I'm excited that they try to push, and maybe that's what we should explore. But I'm with you. It's not enough just to publish. It's somehow you would like to show that you solve problems that are relevant and other people are interested in, and that also requires engineering. So that's why in Darmstadt with the Hessian AI, this Hessian AI Center, we really say, okay, we want to work all. We got this. Well, we will hire then over the next 3 years 20 new AI professors. And we want to really go for the third wave, but actually targeting on what we call systems AI, because I think we need more of software engineering in AI, but also AI for software engineering. But in particular, what does it mean at all to do software engineering for an AI system? And then you will naturally get into what we just discussed because you want to have good quality code and you would like to have maintenance over time in a sense and not just for the next paper. And they're teaming up with companies that are happy to share in an open source fashion. I think that's a good start, but definitely, yeah, I'm looking forward. It was just the last 2 years with setting up or getting these the center and everything. I'm looking forward to start working on that. So I'm happy. Let's stay in close touch, and I will also try to set you up with Moham, and let's see what we can do.
Okay. Okay. Thank you, Kristian. I don't think there are any other takers for questions, so I will probably just end with another round of applause. Thanks very much for taking this invitation and sort of accepting this and giving this nice talk. And we will talk later. Martin, I think we can